discuss something about this carbon nanostructures. So carbon nanostructure is, let's say, one of the, or carbon in a sense, as a material, materials based on carbon atoms are quite used quite a lot in many applications, and the research on carbon based materials actually spans all disciplines. So you go to physics, chemistry, materials, any engineering discipline. Carbon is like a universal element, and carbon based materials are used quite a lot in many applications. Okay, so you talk about uh, like from the bulk to its nanostructure, all kinds of different forms of carbon are used. And so that means carbon has when you look at its structure, so you can have a 3D form or a bulk form, which you have like your graphite and diamond. That is the well-known carbon 3D structures, right? So graphite is quite well known, or diamond is also quite well known. So then you can have also 2D, two-dimensional carbon structures. So like for example, graphene or graphene oxide. You can also make a one-dimensional form, so which is a carbon nanotube. It can be a single wall nanotube or a multi-wall nanotube. Okay. You can also have a zero-dimensional carbon structure, so which is known as Fullerene carbon dots. It can also You can also have a carbon dot. So now also people are making graphene quantum dots as well. Okay. So you can also have a graphene quantum dots. Oh, yeah. So all these different forms of carbon you can have from a three-dimensional structure to a zero-dimensional structure, and based on their, like whether they're a bulk material or a nanostructure, so you can have various applications. So we will go through one by one of these different structures, and normally when we talk about these different carbon structures, sorry, so I'm too fast. So these are known as allotropes of carbon. Okay, what is allotropes of carbon? Allotropes means, so they are different or distinct uh, structures with distinct physical or chemical properties, but they are made of the same element or same atomic material or same compound. So this is like here we have carbon, and so the allotropes of carbon are like carbon nanotube or graphene or even diamond, graphite. So all these are allotropes of carbon. So they have all different or distinct structural forms, and also they behave. So their properties, when we talk about their mechanical properties or optical properties or electrical properties, all are different or distinct as well from one structure to another structure. And this is like a rich field you have, where you can have various kinds of allotropes of carbon. So carbon, that is your carbon atom, so which is the basic building block here. And It has like the ground state electronic configuration 1s2, 2s2, 2p2, and it can also have some isotopes as well. So carbon isotopes also exist, which is normally used like in these isotopes. You can use it for, I mean, they're radioactive, and so carbon tracing. So you can trace the age and so on in archaeological surveys as well. So if you have a carbon atom, that is one thing, but then you have to build a structure out of it by putting these carbon atoms together, and for that you need a bonding. And so the nature of bonding with carbon also can vary, and that is what gives rise to different structures. Okay, so what are the different bonding that is possible? So when you look at carbon, so the ground state is of course 1s to 2s to 2p2, but then you can also possibly have a hybridization, which will lead to a different kinds of bonding. So like you can have sp3 bonding, sp2 bonding, or sp bonding, and that will give rise to different excited states. But this hybridization will lead to some kind of chemical bonding with other elements or even with carbon itself, uh, and lead to this formation of different uh, allotropes of carbon. And what this bonding leads to, so in the right hand side what you see is like for different hybridization, so you have different geometries as well. So you have a tetrahedral geometry for sp3 hybridization, you have a planar trigonal geometry for sp2 hybridization, and a linear geometry for sp hybridization. Okay, and that leads to these different structures. Okay, structural forms of carbon. So for example, when we look at sp3 hybridization, so you have this diamond structure, right? So it's a fcc lattice or fcc Bravais lattice, where you have carbon atoms with sp3 bonding. And diamond, as you know, is like one of the hardest known material in the world. And so it has this tetrahedrally coordinated sp3 carbon atoms attached to each other, and they form this Bravais lattice, FCC Bravais lattice. Then if you take a sp2 hybridization, so you go to a graphite, which is quite well known as well. So it has sp2 or trigonal, this pyramidal structure, not this trigonal planar structure in two dimension. Okay, so in two dimension it is a planar structure, and this is sp2 hybridized. It's a like a honeycomb lattice what you have here. And then when you go to a three dimension, graphite is a three dimensional form. In the third dimension, it has a very weak van der Waals interaction, and therefore it is almost like a layered structure what you get in graphite. And so you have these sheets of two-dimensional carbons, so in graphite, so and that is the name why this two-dimensional form is known as graphene. And they are these layered structure. So one layer is a graphene layer, and then in the third dimension it is like a layered of many such graphene layers, and you get a graphite out of that. And then this is a different structure, of course, as you can see here. and and graphite is like very brittle. It is not like hard like carbon, sorry, diamond. So diamond, all, I mean, diamond and graphite both are from the same carbon atom, but different structure, how they are bonded and they are arranged. So that leads to very different physical or mechanical properties in this case. And in fact, due to this layered structure of graphite, so you can peel it off and you can get this graphene, this two-dimensional graphene out of it. And again, when you look at also the optical properties, that is also different between diamond and graphite, for example. So diamond is like transparent, and but graphite is like very opaque and doesn't transmit, so it looks dark, right? Very different optical properties they have. And even the electrical properties also. So diamond is basically an insulator, but graphite can be is actually a relatively good conductor compared to diamond. So you have a electron transport, or you can have uh, a conductivity along this two-dimensional layered structure. Okay, and that is why you have it has some electrical conductivity. But then out of graphite, so you can make these different forms by, so if you take it one two-dimensional layer, so you get graphene, and if you roll this graphene into a tube, so you get a carbon nanotube. And you can also get a very another interesting structure, that is fullerene, which is almost a like a cage like structure you get again from the carbon, uh, from the, so some form of graphite. I mean, it is not like a graphite form, but why it is put here is because all these have this fullerene, carbon nanotube, graphene, they have this sp2 hybridization. Okay, so you can also have or it is expected, or theoretically that is predicted, that you can also have this linear chain sp hybridization, and which is known as a one-dimensional carbon chain or carbine, which is still not experimentally has not been found yet. uh, but most likely it might be present. Okay, so someone can synthesize it by some chemical route, because when you look at these carbon structures, so the bulk structure diamond and graphite were quite well known for a long time. Okay, but these nanostructures of carbon has been actively kind of research for last, let's say, 30 years or 40 years. So fullerene was first observed or kind of discovered in 1985, and very interestingly, it was found when people were searching for it in interstellar space. So it was not really synthesized in the lab in the beginning. So people were looking at the carbon, uh, because you find, like, I mean, for nature, if you want to look for lives outside earth in different like in space, so first thing what one looks at is carbon. Okay, if carbon exists or not, because that is like a form which is like our life is based on a lot of carbon based materials, like, I mean, carbohydrates, I mean, whatever you talk about, it's mostly has some kind of carbon in it. So all the life forms have carbon, and therefore people look for carbon in the interstellar space when you are looking for living beings. And during such kind of expedition, so fullerene was surprisingly was discovered, because it was not like so at that time, so it was not matching with any of these like known carbon allotropes at that time, so basically diamond or graphite. and this fullerene was discovered that time by Proto uh, in 1985. But I mean, later on, it can also be, it was synthesized in the lab. So similarly, carbon nanotube was not discovered until 1991. Okay, so it was synthesized again in the lab in 1991. And graphene, of course, was like people were thinking this two-dimensional structures are not really thermodynamically stable. So so study on graphene was almost, I mean, people were studying graphene as a two-dimensional layer in theory, like from 1950s, but it was like nobody thought one could ever experimentally realize this graphene, because it seems like two-dimensional materials are normally are not thermodynamically stable. But then in 2004, uh, the two-dimensional form was uh, kind of accidentally found in the lab, okay, where it was like peeled off from just like a piece of graphite, and then you could actually get and graphene was kind of accidentally found in that way in the lab. And then lots of, I mean, big so everybody kind of jumped into this graphene research, and then again lot more many more 2D materials were also discovered or realized afterwards. So this graphene kind of opened the gate for new 2D materials. Yeah, so this carbon graphite structure and diamond structure I already discussed. And when we go to this nanostructures, so we have this nanotubes, we have fullerene, and what is interesting is you can synthesize it in really like a big in huge amounts. You can produce them quite cheap and quite easily, and that's why this is also interesting for applications, because you can make a large scale synthesis of these carbon nanotubes or fullerene or even graphene, uh, and that's why they are interesting for, they're cheap and interesting, and of course they are very interesting physical and mechanical properties. I mean, if you look at their uh, mechanical properties, uh, so all forms of these carbon structures have very unique and different properties. Okay, so in terms of like their stiffness, their Young's modulus, or their resistivity or conductivity, even the magnetism, their optical properties, all are very distinct, and they can be used based on their, like your application. You can use it in different fields. Okay, so you can use it in even energy generation in solar cells, in energy storage, in catalysis, in sensing. I mean, all kinds of possible. You can use it for like in agriculture, or you can use it for water filter. Uh, I mean, many applications which were never thought about are actually people are using this different carbon nanostructures. Okay, and this field is still kind of uh, very interesting. Although, let's say from once this graphene was introduced, so the research on carbon nanotubes for particularly for electrical uh, or for devices, these carbon nanotubes are not much used actually. But like until 2000, uh, people were all talking about that carbon nanotubes are going to really replace silicon based devices very soon. and then graphene came, and then people are actually again talking about that graphene will probably replace these silicon-based devices in near future. But still, going from the lab, from the research lab to real application is takes quite a lot of time, and it is very difficult to replace silicon, because the silicon based devices are really kind of established, uh, and very difficult to compete with silicon based uh, devices in terms of for industrial scale applications. Okay, but in the lab they're still very interesting, and graphene and many other 2D materials which I shared, like few of the review paper. So some of you have already submitted uh, your comments or observation on that, uh, and which is not graphene. Okay, so many more, probably also many new materials can also be discovered in future 2D materials as well. So fullerenes are basically like what was discovered. This fullerene is the C60. So you have 60 carbon atoms in it, but that is not only the carbon nanostructure you can have. So you can have 20 or 24, 28. So different number of atoms you can form, and you can get. So this is like a class where C60 is kind of the first which was kind of discovered, and most studied this fullerene material. Okay, so these are all, like, you can have this closed kind of zero dimensional object, so with 20 atoms or 50 atoms or 60, or you can even go to higher numbers, so 70 or 80. So this number of atoms you can also have, and still they belong to the fullerene class, so zero dimensional carbon structures. But C60 is quite famous because of it's also I mean, one thing is you can actually dope these carbon or these fullerenes with different some other atoms. For example, you can dope it, primarily it is doped with nitrogen. Okay, so nitrogen doping is quite common. You can get very really different chemical properties out of it. Okay, and the structure, when you look at, it's like so you have 32 facets. So when we talk about this C60 fullerene, so you have 32 facets where you have 12 pentagons and 20 hexagons, and it almost looks like a football or a hockey ball. Okay, so that is why it is known as a hockey ball, uh, and looks like really like a football in terms of its shape. So it has 12 pentagons and 20 hexagon, and like each point in the polygon, so you have a carbon atom, and this is all sp2 hybridized. So why fullerene is interesting? Because it has a very symmetric shape. So it's when you look at the shape here. Yeah, so you see here, it's almost like hollow in the center, and carbon atoms, it's like forming a shell, and it is almost like a cage-like structure you have. Okay, so it is a symmetric shape, and it has, of course, a large surface area. Okay, then it also has magnetic properties as well. So it has a Curie temperature 33 Kelvin. So it is actually a very soft ferromagnet. So one of the most common organic ferromagnet. And then you also have a, yeah, high, I don't know what is this high temperature, why I wrote that. Yeah, I mean, yeah, because it can withstand a high temperature, quite stable. Also, it can withstand high pressure. Okay, so it has good heat resistance. It can also be superconducting as well. So it shows this fullerene is kind of shows all versatile kind of applications, properties it has, and therefore it people used to think it. So this zero dimensional form can be used for like organic solar cells, or you can use it for detectors as well. Like you can generate a current, photocurrent, so you can use it as photo detector. Of course you can use it as a catalysis, because the surface bonds, which are these incomplete dangling bonds, so are quite reactive. So you can also make it functional as well, and that is why this doping can be done. This nitrogen doping you can do, and also they can be used also in biomedical applications as well. And also this hollowness also gives, like you can capture particles inside this uh, fullerene in this form. But these are all still based in the lab. Okay, so all these applications, whatever has been proposed, all has not really been translated into a real industrial scale application yet. So you can also, what is interesting is you can also use this fullerenes as building blocks to build large crystals as well. So what you can have is a very weak van der Waals interaction, and then you can make these crystals out of it, van der Waals crystal, which where fullerene is your building block, uh, and that is also quite interesting. So it shows a superconductivity as well. Of course, you need to dope it with different. Yeah, so this doping leads to this superconductivity, as you can see here. So carbon itself, this fullerene is not really superconducting, but you have to dope it with potassium or some other elements to get superconductivity out of it. Although the TC, this critical temperature, is quite low. Okay. Uh, Now, if you go to carbon nanotubes, sorry, too fast. Yeah. So we have carbon nanotubes. So when you have a two-dimensional graphene sheet, okay, and then you roll it up, so you get a single wall carbon nanotube. So typical diameter is can vary from 1 to 10 nanometer. And what is very interesting is this length that can go from a micron to even centimeter. So you have a huge aspect ratio that is you can get with carbon nanotubes, and that's why these carbon nanotubes are kind of known as like one of the highly anisotropic material that has ever been synthesized in the lab. Okay, so the diameter for single wall can vary up to 2 nanometer, but if you take a multi-wall one, so the diameter can go up to maybe 20-25 nanometer. uh, and this multi-wall carbon nanotubes are actually you get due to this van der Waals interaction again. And this length, like as I said, the length can go up to centimeter or micrometer, so the aspect ratio is can be 10,000 or can be more even. Okay, so that means the height to the length ratio. So you can of course get the single wall or multi wall, and interestingly, so you depending on this how you roll it, so you can get a metallic or a semiconducting properties. Okay, so it can be a metallic carbon nanotube or it can be a semiconducting. So we will see how in which when these nanotubes become metallic and in which under which condition they can be semiconducting. Okay. So of course, then when it was first produced in 1991 by Lijima. Okay, so these so first actually it was not the single wall was not produced, it was a multi-wall carbon nanotube was produced. And typically these carbon nanostructures are synthesized. You take normally these electrodes, okay, carbon electrodes, and you apply a high voltage across it, so you have a discharge, high voltage discharge, and you do it normally in an inert atmosphere, so either helium or argon atmosphere, and you get these different nanostructures. So mostly, so not graphene, but you get this fullerene, you get these carbon nanotubes. Okay, uh, so just by taking this the electrode, carbon electrode, and you apply a high voltage discharge, so you get this. So when you burn, let's say like a cotton, so you get this sorry, this suits, carbon suits, okay, and very similar that process, but there you don't get really this nanostructures, but in this inert atmosphere, if you do that, so you get these different nanostructures you can produce, which is quite easy to produce, and therefore you can produce it in a bulk amount. So these are some of the pictures which you see here: the single walled, then double walled, so you can have triple walled. So basically, if you have more than one wall, so more than single wall, so you can call it a multi-wall carbon nanotube. So even you can have multi-wall carbon nanotube with more than 100 nanometer diameter. Okay. So again, in one single wall carbon nanotube, the bonding is sp2 hybridization. But again, due to the van der Waals interaction, you get this multi-wall carbon nanotube as well. So these pictures here, so basically these are some high resolution TEM images, so electron microscope, where you see like a single wall, again a double wall, triple wall, and a multi-wall carbon nanotube. Okay, so these are the real electron microscope images, and this is how these carbon nanotubes normally look like when you look it under a microscope. So you can see the scale here, so it's like 5 nanometer. Okay, so very small diameter. Okay, and it can go up to, for a multi-wall, it can go up to like several, like 20 or 50 nanometer. Okay, so you in carbon nanotube, so short
So,
form, yes,
so, so
yes,
all these phenomena, yeah. So all these phenomena are happening in the presence of inert gas or something else.
inert gas, yes, yes, yes. Normally, it is you produce these carbon nanostructures in inert gas atmosphere. So either helium, or you can do also in vacuum. Okay, so if you don't want any inert gas, so you can also do it in vacuum as well. I mean, these are like the earlier methods how it was prepared. So you can also prepare using this like chemical methods like CVD growth, which is again a very different way of preparing these carbon nanostructures. But CVD is not really. I mean, if you want, you can grow these carbon nanotubes as well. Uh, but then there the method of synthesis is very different. It's a chemical reaction that is going on, and But again, you cannot, let's say, so for many device applications, probably you would like to synthesize using CVD, because you can have a very good control over over which type of carbon nanotube, for example, you want to synthesize. So let's say when you are doing this discharge technique, so you can get many kinds of mixtures. Okay, so you can have some carbon nanotubes. You will have single wall, some will be multi wall, double wall, triple wall. So all mixtures can be there, which is not so easy to uh, separate. Uh, but in the beginning, when people were using it, so you just because it was quite cheap or easy to synthesize, so people used to do that. Okay, so this discharge, arc discharge, or you can also do it with a laser, like exposing it to a high power laser as well. Okay, so that is another way. uh, yeah, so synthesis can be done in different ways as well. So not only this uh, high electrode discharge in an inert atmosphere. Okay,
Yeah.
does that answer your question? Or
Yes, sir, got that.
okay. So carbon nanotubes are actually defined in three different uh, like like an armchair carbon nanotube. So you have multi-wall and single wall, but then how you fold it, so depending on the folding, so we will see that. So maybe, yeah, so next class. So we'll have a armchair, or a zigzag, or a chiral kind of nanotube. Okay, so these are the three forms of nanotubes typically you get in nature. Okay, so next we will consider just a little bit about graphene. So graphene is nothing but again a two-dimensional form. So something delay there is. So graphene is like a two-dimensional form of this is the 2D form of your nanostructure. Okay, so which is basically has a sp2 hybridization again. And what is interesting is, like, you have, as we discussed before, so you have a 2s 2p2 state, so 2px1 2py1, and 2pz is kind of empty. But if you have a this hybridization, so between 2s 2px 2py and 2pz, so you can have a hybridized state, and you get a covalent bonding you can have. uh, yeah, I think this part I will skip. Anyway, I will share this slide so you can go through it, because it is not interesting for everyone. So I'll just skip this part here. It is only about like how you get this sp hybridization. Like you can calculate different like quantum mechanical states, which will give rise to this sp2 hybridized state. And basically, it is a honeycomb lattice you have. Uh, so do you see that? Okay. So what you have is a honeycomb lattice in graphene. And so the Bravais lattice is a triangular Bravais lattice. So I think this is one of the problems in your assignment. So you can do that and find out what is the reciprocal lattice looks like. And then you also have, when you go to the reciprocal lattice, so this reciprocal lattice will give rise to or tell you about your band structure actually. And normally, like when you look at silicon, for example, So silicon, as you know, is an indirect band gap semiconductor. So gallium arsenide is a direct band gap semiconductor. Okay, but graphene is actually is not a it's a semi-metallic. Okay, so kind of it has a zero band gap material because of this unique hexagonal lattice. Okay, uh, I will not really do not want to really go into the discussion here band structure. So if you are, I will anyway share this and you can go through this band structure. But what is interesting in graphene is I want to show that what is a little bit lag. Okay. Yeah, so the graphene band structure is unique because you have a point known as this Dirac points where your conduction bandage and valence bandage kind of match exactly, so they are degenerate. So therefore, there is no band gap basically, and you have six such points, so Dirac points in your graphene band structure, and that is why it is a semi-metallic kind of mm, material. So you have no band gap there, and that is actually one of the reason why graphene. So you can create a band gap by applying a electric field. So that has been done, experimentally been shown, but that is also kind of restricts application of graphene in real devices. Okay, or many optoelectronics devices. So here again one can use like a how one can calculate the band structure, so that has been discussed, so I'll skip that. If you want you can go through, but the tight binding approach shows how these Dirac points, these six Dirac points, they appear in graphene, and also experimentally that has also been verified as well. So this Dirac points you can also observe using this ARPES angle resolved photo emission spectroscopy. So you can actually observe these Dirac points in graphene as well. But that what it leads to is very interesting uh, electrical properties of graphene. Okay, uh, so what is like you have really high intrinsic mobility. So when we talk about devices, so we always talk about what is the mobility electron or the charge carrier mobility in it, and the charge carrier mobility is quite high, up like 200,000 or like 2 lakhs centimeter square volt per second, and then a huge Young's modulus. Thermal conductivity of graphene is quite high. Also, like yeah, of course, the optical transmission, it transmits everything, uh, and that's why this is very interesting 2D material, and particularly because of this high intrinsic mobility, people were very interested in using it for devices, and then thought that this could really replace silicon based devices. But then these are all still like intrinsic mobilities. Okay, so when you make devices, then there are a lot of other factors which comes in, which reduce the actual mobility, charge carrier mobility here in graphene. So another interesting thing of this why you have this high intrinsic mobility is because you have this charge carriers are actually almost behave like a relativistic quantum particle, and therefore they have this huge mobility you have. So almost they move in a ballistic manner. Okay, So almost there is no, like, as if there is no. um, so these charge carriers, which are responsible for electrical conductivity, are almost known as a massless Dirac particles. Okay, so therefore they have very huge mobility as well.